Now let's look at our oscillating motion in a little more detail. So if we have for example, a mass on spring system that oscillates up and down, and we'll continue using this as our example. We know that, if we draw a little like cartoon of what happens, we start by pulling our object down some distance below its equilibrium position. So if this is its equilibrium position, maybe we pull it down like this, we let it go, so it ends up here with a velocity up, and it ends up getting to some height, and then it, falls back down and ends up at some lower height where the spring is stretched. So of course, for the real system, as time goes by, it slowly loses energy, but in terms of, if we ignore that loss of energy, it's going to continue going, oscillating, from down to up from down to up, indefinitely. Okay, so it turns out we can draw a graph of what this motion looks like. And it looks like this. So we'll use x as our position variable. We could use y or something just as easily. What we call this isn't important, but we'll call it x for now. And our position as a function of time looks something like that. So this is its equilibrium position here, x equals 0, and it's above it, and then it goes down back to where it started, and then goes below it, and then goes back up to where it started. So this function, this looks like, and we could guess correctly, that it is a sine function, or a cosine. We'll say it's sinusoidal, right? So that just means it is sine or cosine. And this is true even though, normally we see sines and cosines when we have circles or things rotating, right? And nothing exactly is rotating here, meaning moving in a, moving with circular motion. But it turns out the math works out exactly the same as if it were. So this math works out to be this sinusoidal motion. So what is this equation? Like, what can we write down for this equation? So we know it's going to be a sine or cosine function. We know it needs to somehow involve the frequency or period, right? Since that determines how long it takes it to undergo this oscillation. And we also need to know something about this amplitude, like how big is our oscillation. So we can label some things on here, right? So this time it takes, so this from equilibrium up, down, and back to equilibrium, this is one period, capital T. And this value here, if this is x equals 0, then this position we could call x max, or sometimes it's called x naught. This is our amplitude. This is telling us how big the oscillation is. So from this picture, we can pretty much write down an equation for what our oscillation looks like. So this is x, our position as a function of t. So x of t is equal to our amplitude, which we'll call x max. Like I said, sometimes this is called x naught, but we'll call it x max. X max times the sine of 2 pi f times t, where f is our frequency and t is our time variable. We also could write this as 2 pi times t over the period, since f is 1 over t, so these two things are interchangeable. We could put either one of these inside the sign if we wanted. And it is very, very important to note that this sine function is in radians. So this is really the only time we're going to use radians in Physics 106. And that is because this 2 pi is, in radians, this is one oscillation. And that is getting multiplied by f times t. So remember, this is also equal to t over capital T, the period. So this is like the number of oscillations or fractions of an oscillation that have happened. So we're this number of oscillations or fraction of an oscillation, we're multiplying it by 2 pi, and that's how many times we're going around the sine function. And so that's how this works. So this sine function has to be in radians if we're using this 2 pi, because 2 pi is one oscillation in radians. Okay, great. Awesome. So there you have it. This is our equation for the position. So when our position, so if we look at this motion of the little mass on spring, we can see this motion happen with our eyes. We can see how its position is changing as time goes by. What we can also guess at is that while this is happening, the velocity is also changing, and we can be very specific about how the velocity is changing. And in fact, what I'm going to do is I'm going to make another graph here to show what's going on with our velocity. So we're going to use the same time axis and the same, we're going to draw the velocity for this x graph here. So without doing any math, really, we can look at this graph and say some things about what the velocity should be. So in other words, like when we're at this highest point, anytime our object is at the highest point of its motion, we know that at that point the velocity has to be 0, because if that wasn't, it wouldn't be the highest point. So in other words, here our velocity has to be 0. Here our velocity has to be 0. It also has to be true at the lowest point. If the velocity isn't 0 at the lowest point, it wouldn't be the lowest point. So these have to line up. These zeros have to line up with the minimums and maximums of our position. Okay, we can also do some things like, well, here our function is going from x equals 0 to positive x the whole time. So our velocity has to be positive, right? We're going up. So our velocity has to be some positive number up here during this. Here our velocity is going, our position is going from some positive value down to some negative value. So here our velocity is negative the whole time. Here, negative value to positive value, our velocity is positive the whole time. So this gives us a sense of what the shape of this graph is, and we can fill in the rest. So our velocity graph actually looks a lot like our position graph. It is just shifted over by a quarter of a period. So our maximums here and our minimums happen where our position is 0. So our maximum velocity happens when our object is at its equilibrium position. We could do other things to show why that's true, but it's enough to get that information from the graph for now. So in addition to our equation for this x, we also now could basically write down an equation for what v looks like. So v of t is equal to some maximum velocity, v max, times a different trig function. So here it's not a sine, but a cosine. So this is v max times the cosine of 2 pi ft, where the cosine also has to be in radians, just like the position did. So we have an equation for position, an equation for velocity, and we'll do an equation for acceleration. I won't derive this one, but we could use exactly the same logic about the v graph to get the a graph. But I will just skip to the end. It looks like this. I just want to make sure it lines up right. Yeah, that's good. So our acceleration equation is a of t equals a max, our maximum acceleration, times the sine of 2 pi ft. But notice where x is positive, a is negative, so we need a minus sign there. Okay, so we have a graph of our position, a graph of our velocity, and a graph of our acceleration. So if we know any one of these, we can figure out the other two. And that is true for any point in time. So if we have some, if we want to find our the height of our mass at time t equals 3 seconds, we can plug that t equals 3 seconds into our equation and say, oh yeah, its position is exactly this, and plug that same 3 seconds into our velocity and our acceleration equation to get those values at that time also. So this turns out to be handy if we're trying to figure out the position or velocity of objects at a particular moment in time.